going to invite kind of an adventure surveyor in to talk to us, but we're going to hear a little bit more about the high precision GNSS is helping in philanthropic efforts in different parts of the world, and in this case through the Engineers Without Borders. So I want to introduce John Hamilton, a geodetic surveyor. If I actually listed all of the areas of expertise in surveying and geodesy for John, I'd be going on and on and on. Known John for many years, and he's actually helped me out with structural monitoring questions. John does, his company Terrasurv does a lot of structural monitoring. Actually, I think you're out of town at a dam site right now, and I think working from the cab of your truck through a hotspot. But John, welcome aboard, and we look forward to hearing about how you've supported Engineers Without Borders, and also another subject that's being discussed today. Another innovation is the L-band PPP high precision GNSS for areas without real-time networks and without cell coverage, which is a lot of the places you worked. Welcome aboard, John.
Yeah, we're actually at a couple of dams in Tennessee doing deformation surveys this week, and wasn't anticipating that when I volunteered to do this, but here I am in a Walmart parking lot where I got a good signal. As Gavin said, we do a variety of projects, a lot of which is dam monitoring, but I also do a lot of LiDAR control, photo control, which brings me around the United States and around the world. What I'd like to talk about today is I became involved with a group called Engineers Without Borders, and it's similar to Doctors Without Borders, where we find projects where we can try and help people that need help, not just out of the country, also in the United States. I belong to the Pittsburgh chapter, and we have a couple of local projects, but we've been working in Ecuador for a few years now, and maybe in Ecuador, and being involved in providing water. So that's what I'm going to talk about today. Okay, so the whole philosophy behind Engineers Without Borders is to try and share our expertise with less fortunate people, less fortunate countries, and try and improve their quality of life. And also sort of a technology transfer. So once we set up a project, a water system, for example, we don't want to have to go back. We want them to be able to run it. So we try and share the technology as well as the knowledge. Okay, so Karinga is in Ecuador, and it's a small community way up in the mountains, 150 years old, has about 200 inhabitants. And it's mainly subsistence farming, but while we were there were very few men. Most of the men go to the cities, do construction work, send money back. The only source of water is a 1,400-foot elevation descent down to, they have a cistern down near the river, and they can't use the river's polluted, but they have to carry all the water back up 1,400 feet in elevation several times a day. So there's Ecuador. The actual community is located almost on the equator. So to the right of the screen, it looks like an interstate symbol. It's actually the Pan American Highway, mainly a 2-lane road. It goes all the way through Ecuador. Right about the middle is Latacunga. That's a fairly large sized city. They have a cores there, but very difficult to get the data. Could not get real-time data from them, and there was no cell service anyway. Karinga is located to the west of that, up in the mountains. So the area I've outlined in red is where most of the houses are. And to the north of that is the water source down in the valley. And you'll see in a few other pictures coming up how really steep it is. But if you look just down to the south end of the red area, you see a kind of a dark area. That's used to be a spring that they depended on. Somebody had the brilliant idea to plant trees there. The trees sucked up all the water. That killed their water source. So after that happened, they had to hike down to the river to get the water. So as I mentioned, there's no cell service. They only got electrical power about 10 years ago. It's very remote. There's no large-scale maps, no control in the area. So what we needed to do was, before we could design the system, we needed to map all the houses, map the source, and especially important was elevations, because this system was going to be pump it up to an upper tank and then gravity feed to all the houses from there. So elevations were very important. So in Ecuador, they actually use Surgas. Surgas is a continent-wide coordinate system, and they actually have yearly meetings, which I went to 2 years ago in Mexico City. Very interesting. They continuously update it because a lot of parts of South America are tectonically active, so they've got earth movements. Ecuador does have a CORS run by the military. It was interesting. After we did this, I went to try and get data, and I had to go to the capital. I had to show up in person, and I had to pay $50 cash to get data for 1 day. There was no FTP, no downloading. And of course, there's no real-time network available. Now, the country also has to deal with, similar to what the US deals with in California, where they have occasional earthquakes causing coordinate changes. The other issue was there was no geoid model, so we had to use EGM-08. Okay, back in 2012, they did a previous project in a nearby community, and they operated constructed a water system, and that enabled the community to build a hostel and to make money off of people traveling through. So we stayed at the hostel. It was very rustic. It was 2 rooms, 5 bunk beds in each room. We had water, but we didn't have hot water. And despite the fact it's on the equator, it's about 10,000 foot elevation. So the weather is always cool, very cold at night, near freezing. So it wasn't comfortable by any means. Next slide. Okay, this is what the community center that they built, and in the background you can see the water tank that was built to service the community. Similar situation, the source is down at the river, pump station, they pump the water up, it goes into that tank and then distributes by gravity to the households. Okay, so this is a 1 to 50,000 scale map, and you can see, maybe a little bit hard to see, but Karinga is where the community center is. We had an intermediate pump station, and then we had the source. So down at the source, we built the main pump, and then at a certain elevation, we had to build another pump, intermediate pump, to get it up to the tank, which was above the village. So I said it's about 50 degrees south. It's interesting because between here and Quito, which is about 0, so about 20 degrees south latitude, I actually was hiking in snow on top of a mountain. So there's snow all year round in some areas. Anyway, so what we did, we visited each house walking because there's no roads to the houses. Nobody has cars. This is a village. They just have a few animals. We got a position at each house so we could plan the route. We profiled the pipeline route, located the roads and the ravines because we had to cross several ravines and we needed to know where we might need reinforcement to cross them. I also set control points at the source pump house, the intermediate pump house, the upper tank, which is where all the water was going to be distributed from, and also we set a point at the community center in case any future use. So this is just a quick snapshot of the tank that was designed by us. And it may be hard to see, but if you notice, all the dimensions are in both meters and in metric system and English system. So it was built by locals, so we had to put the metric on there. But this is basically what it looks like. It had a sedimentation well, and it had a pump, and pretty simple. Okay, this is a pipeline profile. And if you notice at the bottom, the total distance is only 6,200 feet, yet it goes up from about 10,400 up to above 12,000 feet in only 6,000 feet. So extremely steep. The flat area, once it flattens out, about in the middle of the diagram is where the community is mainly located. So there were 5 critical points that we had to locate, both horizontally and vertically. And first of all, of course, the pump house. The next one is, because of the high pressure, we had to use metal pipe from the pump house up to a certain elevation where the head loss would create lower pressure so that we could transition over to PVC pipe, which was much cheaper. Then we had the intermediate pump house, which we also located in elevation based on design of the pump and the head. Another transition, and then finally the upper tank, which was above all the houses so we could have gravity flow. So there was 5 critical points that we used in the design. So everything was done in UTM coordinates, and I call them EGM08 elevations. Basically, it was ellipsoid heights from ITRF and using the EGM08 model to get elevations that water would flow. And we also computed all our distances on UTM. We used an Excel spreadsheet that some of the engineers had to iteratively determine where the best location would be based on the design parameters of the pumps and the head losses and that type of stuff. So this shows where all the houses are located. So you can kind of see they're spread out. But basically the water is going to go from the source to the intermediate pump to the tank, and then from there by gravity. So the actual pipe from the source up to the tank was pretty small. I believe it was 2-inch pipe, and it was going to pretty much flow constantly, but keep the tank filled up, and then at times of peak demand, the tank would drain down somewhat. So where do we get the contours from? That's from the SRTM, the Shuttle Radar Topography Mission. It's not super accurate, but it at least gives us an idea of what the terrain looks like. Those contours were 20-meter contour intervals, so 66-foot contour intervals on the map I just showed. So this is the high point up by the tank, a little bit above the highest house, and that black area in the middle, that is the trees they planted that killed the existing spring. And we'll see in another slide here that there was quite a bit of water flow, because you see a deep ravine coming out of there, but there's absolutely no water flowing out of there now unless they get a heavy rain. So this is what it looks like, and you can see the trees up in the upper left, the tank location, and then the first house is right about in the middle. And they pretty much grow potatoes here. They gave us all our meals, they cooked all the meals for us, and it was pretty much some form of potatoes, potato soup, potato stew, everything was potatoes, some meat thrown in. It's too high up for cattle, so they had sheep. So basically it's subsistence farming with potatoes, which they sell in the market. So this is a typical house, nothing fancy. The plan was we were going to come to each house, put a yard faucet right there, and then they would have water. So it's not indoor plumbing, there's no sewage, it's just to get water to the houses so they don't no longer have to haul it. And here's kind of a picture that the containers on the ground there in the lower left, that's what they use. They would hike down, and this would occupy a good part of their day, because it would take an hour to walk down there, fill up these containers, walk back up twice a day maybe. They also used a lot of large containers to try and catch rainwater. Here's another picture. You can see they're collecting it off the roof. They've got it going down into drums to try and get as much water as possible. It never rained the whole time I was there, so that's only a solution for part of the year. Being so close to the equator, they don't really have seasons. There's not a summer, winters, fall, and spring. It's more of a rainy season, dry season, and the rainy season is not very long. So they cannot depend solely on rainwater. So if you can see in the middle of this picture is the ravine going down that used to have water in it. But this is pretty typical of the terrain. They pretty much farm all the land they can or graze animals on it, and they rotate their crops, of course. In the upper left of the photo is the community center. This is a picture of down the pump house. To the lower left is the river. We found a good quality spring coming out. We captured that water, and then in the middle of the picture is where they're starting to build the pump house. So to me, this was the most fascinating part, is that all the materials for the pump house and the intermediate pump house had to be carried down from the community center, which was the end of the road. There was 420 large concrete blocks, sacks of cement, rebar, formwork. Everything was carried by women, llamas, women on their back. I saw a woman put 50 kilograms of cement on her back and a baby on the front and hike down to the site. So it was just amazing what they could do. So this one here, they're loading up the llamas, every single thing. And at that point, there was no electricity down there yet. So the electricity had not been run in yet, but we just had to hike down. It's about an hour walk down the hill to get to the pump house, the source pump house. So here you can see the woman carrying rebar down. They'd already made, I wish I knew how many trips they'd made, because it was a phenomenal number to get all the materials down there. And to them, this was nothing. They wore shoes, flat-soled shoes, slippers. They would go up and down this hill like nothing. The first time I went down it, and went back up. I swore I would never do it again, but when they started pouring the concrete, I decided I had to go back down. But it was extremely, extremely steep and high altitude, above 10,000 feet. So this is looking down into the river valley. So the pump house is down at the very bottom, and you can see across the valley on the other side, they've got cultivated fields that are really steep hillsides. Okay, this is down at the pump house. These are all the concrete blocks they brought down. And like I said, there was a couple men there. Most of the men there were with us, but almost all the work was done by the women. So here they're building the formwork. The plywood forms we had to bring down, but the actual supports that would look like 4x4 beams, they cut those there on site. And you can see most of the women have a baby on their back while they're working. So they mixed everything by hand. Of course, the day that they decided to pour, it did rain. They couldn't stop because they had to make sure the water, that the tank was one single pour, concrete pour, so that it wouldn't leak. So they just had to keep going. And they actually worked into the night finishing the concrete tank. So this is how they got the concrete over. Just a bucket brigade, passing buckets back and forth to get the concrete into the forms. This is the intermediate tank site. So based on the calculations we did with the Excel spreadsheet, we decided, okay, this horizontal location, vertical location, this is where we need to put the pumps. We started digging, we got down about 2 feet, and we hit a huge granite boulder. And we tried everything we could to break that, and we wound up having to move it a little bit. But we spent probably half a day there trying to dig down through. So once we got all this set up, the whole community got together, made a special lunch for us, brought us cakes, sang songs, made speeches. So it's very good. Unfortunately, we still have not finished the entire project because we had to wait for electricity to be run by the government. And that took almost a year. They finally got electricity. The upper tank is built, and we're waiting to connect the pump. We had planned on going back down earlier this year, but of course the pandemic cut short all the trips. Next slide. I think that's all I have for that. So the other thing I want to talk about, I went back about a month later after that trip with a group of surveyors mainly from the Northwest United States. And we were trying to go down and retrace the first geodesic mission, which was done by France in 1735. They sent one group of people north in Europe and one group to the equator to try and determine the size of the Earth and whether the Earth was an oblate spheroid or whether it was bowed out at the poles. And they went down having no idea what it was going to be like in Peru. It actually took them 8 years to do this. But their measurements did lead to the original definition of the meter, which is 1/10,000,000th of the distance from the equator to the pole. And to this day, it's still very, very close to that number. So when we were there, we went to the hacienda that they stayed at in the 1700s. We took some RTX measurements, which, as Gavin just mentioned, is the real-time PPP over a geosynchronous satellite link. And we found a disk set in 2005 by the Ecuadorian government on the equator. And our real-time position was about 24 centimeters away from that. And as it turns out, we go and get data from the cores. It turns out that's the velocity of the plate in that area. So the equator is not a fixed point on the ground. It's going to move over time. And we had hoped to find some stations from the 1700 network. It turns out that the baseline that they measured, they had 2 stations nearby. They were just destroyed about 5 years prior when they built a new airport in Quito. So we didn't find anything there. This was at the hacienda. They've actually got a terrain model, and this is the chain of triangles that they measured in the 1700s. Took them years to do this, to try and determine the figure of the Earth. So I think that's all I have. One more slide, I think maybe that's it. Yeah. Oh, Okay, I'm sorry. So this is I actually went to Ecuador in 2012 prior to all this and visited the touristy equator thing. It turns out that's nowhere near the equator. It's 100 meters away. This location is where the actual equator is right now, geodetically correct. So this line that you see going up the middle, that is the equator. So this is using RTX, where the ITRX or the ITRF 2014 0 degrees of latitude is. And you can see it's offset from the vertical line that marks the equator. Doesn't mean it's wrong, it just means that it moved since they set that. So what we wound up doing with NSPS, Hemisphere GNSS, Bernsen, we set a new monument right on the equator, kind of a collaborative effort to do this, to set it.
Sure thing. I got a couple of questions myself, and several have popped in. One is, well, a little unrelated to your talk, but you know, the mention that you do structural monitoring at dams. Someone interested to hear your thoughts on using INSAR data, you know, satellite synthetic aperture radar interferometry in conjunction with the data you collect for dam deflection projects.
Well, I think the INSAR is mainly a large area terrain settlement idea. They actually have, one of the dams we work at was undergoing a rehabilitation, and so they're very worried about it moving. They actually set up a radar in a horizontal mode. They had a radar emitter down at the bottom, and the idea was that it would periodically scan the face of the dam and to millimeter accuracy. I wasn't involved in that. I don't really know how it worked, but it's the exact same principle, I think, as INSAR.
Okay. Yeah, we've used INSAR a bit for looking at trends in the foundations of the dams, the adjacent terrain.
Basically, what we're doing here, they have monitoring points set in all the monoliths, and we basically are trying to survey them to 3 millimeters horizontally, 1 millimeter vertically, and repeat the survey over different epochs and try and detect any movement before it gets to be a problem.
Yeah, and achieving those precisions is not as easy as it sounds. Yeah.
Exactly. Yes, that's very, very correct. Very true.
The time series is the proof in the pudding. A little bit about the PPP service that you used. I mean, for those unfamiliar with it, how does that work? I mean, a lot of people that go out with the, mapping unit or survey unit, connected into a real-time network or with a basin rover, we're kind of spoiled because we get both really tight horizontal and vertical. But when you got a place with no cores, or at least the cores continuously operating reference stations that'll let you access the data in no real time. Explain a little bit how the process in the field works with that PPP. I think you were using the RTX at the time.
Yeah, so I use Trimble equipment. Trimble has a service, RTX. It's a subscription service, paid by the year. The correction signal comes over geosynchronous satellite. So in addition to being able to see GPS, you need to see the geosynchronous satellites, which is interesting because we had a potential project up in northern Canada where we couldn't get the corrections because the satellites were too low. They were down below the horizon, so it wasn't possible to do that. When I did this project in the last few years, the RTX, there were certain small areas in the US that had what they call fast init, where it would initialize in a minute. Now, if you're used to VRS, where it initializes in 5 seconds, that seems like forever. But if you're outside of this area, like Ecuador, South America, it would take up to 15 minutes to initialize. But once it's initialized, you can move around, very similar to using RTK, VRS. As long as you didn't lose lock of the satellites, you were initialized. The horizontal accuracies I've always found are quite good, 2 to 3 centimeters. The vertical is a little bit, I would call it 5 centimeter type accuracy for the vertical. But the real advantage is that it doesn't require a cell service. You can go anywhere. I've done surveys in Guyana, up in Canada, different places where if I had to rely on cores, I'd just be out of luck. So it's a very powerful tool, and I maintain a subscription all the time just because you never know when I'm going to be out somewhere, and no cell service. So switch over to RTX and just keep going. The one drawback to RTX, which is that it works on the ITRF coordinate system rather than NAT83. But you can calibrate or you can use a transformation, so you're pretty close to NAT83. In the US, they've recently upgraded the system so that now pretty much all of the US is the fast initialization.
Okay.
Hope that explained it.
Okay. Well, you know, PPP has been around for 30 years, developed in Canada because I was reading up on it. You know, the Natural Resources Canada had to survey a really huge country with little geodetic infrastructure. And PPP takes just the clocks and the orbits, well, initially, just the clocks and the orbits, what refined ones, and you have that convergence you're talking about. But yeah, in the US, where they have the semi-dense networks of reference stations, they can you know, add to the tropo model, or add to the Iono and tropo model, and things like that. Magic behind the scenes that they won't completely reveal, but you get that fast initialization.
Well, interestingly, what I found out from Trimble is it wasn't so much, they had the dense network in the US, it was a bandwidth, satellite bandwidth issue.
Oh,
to get the correction, because it requires more data to get the fast init, and they had only a 600 baud connection over the whole United States. Now they've updated it to 2400 baud, so now they can distribute the data they needed to get the fast initializations.
Okay. And I understand, reading up about the Ecuador trip, that another rover with a different PPP system, I think they used the Atlas, the Hemisphere Atlas, they had done it, and you guys concurred with each other pretty close, right?
Yes, yes. Their system is actually spec a little bit less accurate, let's say, than the Trimble RTX. I'm not significantly, but a little bit less, but it was well within their spec and our spec, so everything matched up pretty well, yes.
Okay, we're going to hear more about these, how PPP services the Albion work. Today's last session, we've got an engineer. I don't know if you've heard of the Veripost system, which I think is now like Trimble Novotel SmartLink or something. But one of the chief scientists on building the algorithm is going to talk later today. So John, you know, it's always fascinating to talk to you about some of your projects. And in survey forums, you give people glimpses, but there's other geodetic things you've done, like you had to put positions to calibrate inertial systems for defense, even inside hangars. I mean, how do you approach something like that?
Yeah, so interesting. This happened first back in the 80s. A defense contractor called and said, "We have these inertial systems. They go on fighter jets. We need to calibrate them inside a building." So we went over there, and they had hired a surveyor to do this, and he traversed in, and they felt that it wasn't matching. So they wanted gravity on the pad, an azimuth, and a position. So the position was, they actually drilled a hole through the roof and dropped a position down from the roof. But to get the azimuth, I had to rent a gyro, which I now own one, but rent a gyro theodolite and get the azimuth inside the building. And interestingly, I just got a call last week from a company near me that needs to do the same thing, and apparently the contractor blasted through the wall so that they'll be able to see Polaris from inside the building.
Oh, wow. Well, you know, earlier today, Joe Paiva showed the picture of the hole in the top of the KC-135 tankers, where the sextant had the periscope on it. Yeah, I remember. I regret not buying one of those at a yard sale once. The sextant with the periscope.
Wow.
Back to your Ecuador project. So you used the RTX. You know, you talked about you had the rough terrain from the well, for your DEM, there was that really rough, you know, 20-meter contour interval. How do things match up? You were able to get, I know that you know, PPP is not particularly strong in vertical. You're talking, 5 centimeter at best. How did things match up with those records?
The mapping we had, so I had topo maps from the IGM Institute, the Military Geographic Institute in Ecuador, who did it with the assistance of the US DMA back in the 50s. And everything matched up to spec. It's 1 to 50,000, 20 meter contour interval. It matched up to spec. So it worked pretty well. Of course, there's a datum issue. I'm using ITRF00 with EGM08. How well does that really match the sea level datum they're using in Ecuador? I don't know. But I would think it would be within a meter.
Oh, okay.
But,
and then
but we were within our site, and there was no other control there, so nobody's going to prove me wrong.
okay. Well, in a lot of ways, your design for the pump and pumping the water just had to be relative to itself.
Relative, correct, relative. But you certainly don't want to use ellipsoid heights. You certainly want to use some kind of a geoid model. And like I said, EGM08, I found relative in a small area is going to be perfectly fine.
Okay. Okay. So another question is you use a lot of different equipment, and there's a lot of discussion here over the next 2 days about the multi-constellation. So give us a little bit about your experiences. I know you, as soon as you were able to get the multi-constellation, you started experimenting with it. What's it been like so far?
Yeah, so what I found, I still do to this day static GPS using just GPS. I found that's the clean, for short lines, that's the cleanest. Don't try and mix anything else in, it doesn't really help. Once we get into RTK, well, VRS, the VRS near where I live does not have multi-constellation other than GPS and GLONASS. So until they upgrade their cores, we're stuck with that. So we do a lot of setting up our own base. We use a Trimble alloy for the base, transmit corrections over cell, and the new Trimble R12 will, when you have 20-some satellites, it'll work in full foliage woods. It's just amazing. I had to prove it to myself, of course. I don't just to where I surveyed very accurately into the woods, and then went in the woods and took readings, and it's really amazing with that number of satellites, the results you can get in just a few minutes. So it's a game changer for us because we do a lot of USGS LiDAR work, and we have to do checkpoints in the woods, a certain number, usually 30 to 40 checkpoints in the woods. Up until this year, we would always set a pair of points, use a total station, survey into the woods. Now we can, a big time saver, just go in the woods, and we set a base nearby. I should mention that. That's critical.
Okay.
We set a base nearby, and we can go in the woods and in a few minutes have centimeter accuracy. So it's a big game changer, I think, the multi-constellation.
Well, you and I see the same survey forums, and we see some of the misconceptions people have is they buy a single rover and that has multi-constellation capability, but hasn't been enabled in the solution as one. And the next one is their base has to, as you said, your base has to transmit. You can't use any signals in RTK or signals or satellites unless that base is seeing and transmitting corrections for the same.
Yeah, and realistically, I understand the VRS operators have invested a lot of money in base stations, and it's hard to just change them all at once. So I think they're slowly changing them, and it'll be in a few years. I think they'll all be multi-constellation, but in the meantime, we're kind of stuck with a hybrid of GPS GLONASS. Everything has GPS GLONASS mostly, except for some UNAVCO stations, but slowly it's getting to be more constellations.
Cool. Well, come on out here. I have one station left out of 138 to upgrade.
Well, I think you're way ahead of everybody.
I would have done it this week, but there was this virtual conference thing, and so, I don't know, commitments, right? So,
absolutely.
Yeah, look at some other trends. Structural monitoring. So, outline that for us. You do it for dams, and I know you do it for locks. What are some of the technologies? Is GNSS being used for some of that?
For concrete structures, which are locks, concrete dams, we do everything with a total station. We also throw in GPS day-long sessions to kind of give it orientation, to kind of strengthen it. But the majority of the measurement, all the measurements on a concrete structure are still done with a high accuracy total station, 1 second, 1 millimeter EDM, which is some, and the other purpose of the GPS is to bring in outside control to make sure that the control we have on site hasn't been disturbed. An earthen dam, we do those with GPS for horizontal. We still run precise levels for the vertical. The accuracy criteria is a couple centimeters for earth dams horizontally, whereas it's a few millimeters horizontally for the concrete structures. And I've seen presentations, I've seen reports where people have done RTK on concrete structures, and to me, it's just not quite there.
Okay. Okay. I'm doing the same on my earth dams as you are, but the concrete ones we have hybrid with total station and GNSS. That's because we also want to be able to differentiate between a regional movement and a local movement. We have tectonic.
And I should add, if you've got continuous GPS on a concrete structure, I think that's very useful. All of our projects, there's no GPS at the site, so okay. it's a one-time thing. So we don't really have the luxury of being able to average the data over a long time. So we typically deploy 4 to 6 GPS receivers on a concrete dam, and then take hundreds and hundreds of measurements with the total station, including the GPS stations, and throwing it all in an adjustment, adjusting it together.
Okay, campaign style GPS. Cool.
Yes, exactly.
Cool. So this came up in a discussion yesterday, and I wanted to see what you thought about it. This notion that with that many satellites in view, if you've got 4 constellations and you've got 4 times more satellites in view, the old thing that you and I learned back in the beginning days of GPS was you had to be able to use an alternate geometry and compare it, set up on a different day at a different time of day, so you had a different geometry. I've heard people propose that with the amount of satellites up there, that might not necessarily have to happen, because you've got a very diverse geometry to start with.
I believe that's true. We always use local based RTK for highway projects, and part of the spec is reoccupy 2 hours at least, different time frames, and we're consistently coming in millimeter agreement, even vertically under a centimeter, which is implying what you're saying. The geometry is not as critical because there's so many satellites. Now, if you had an extremely blocked site with only satellites just directly overhead, that may be an exception to that rule. But I think in relatively open sites, there's not really any advantage to be gained by different time of day occupations.
Cool. And I don't know if you've tried it yet, but on the Access 2020 version, you can actually choose different geometries from the same number of satellites.
Oh, I haven't tried that. Okay.
Yeah, it is. It's kind of fun. I'm still testing it, but these are the possibilities that we have with. It's a whole new world with the multi-constellation. It's blowing my mind.
Yeah, I think one thing that's happening is they've done a very good job of using all those satellites to minimize the effect of multipath. I mean, multipath is the whole key here, and getting rid of the multipath as much as possible. They've done quite a good job at that, I think, and they've got so much data to use that they can throw out anything that's really contaminated and still get a really good solution.
Yeah, and Multipath, on my test sites, one of them is my Multipath hell site directly under a transmission tower. We've got a great point there that was set with digital level and total station. And just within the last 18 months, finally, there's 3 different receivers I've tried in there that actually fixed and nailed that position, that it would have never happened prior to multi-constellation. Oh, we got a late question just popped up. Share your thoughts on mapping of glaciers.
Well, I think the RTX would be excellent for that, because once it's initialized, you could just get a real-time feed out of that. If we're talking about tracking of a glacier, you could have a unit set up and track the movement in real time, and no other infrastructure needed, no cell service. Because once it's initialized, it'll maintain. I mean, I pretty much found I track over a couple of days on my test network, and it'll maintain millimeter accuracy on a stationary receiver.
Wow. So you could set up a receiver with a power source, getting corrections from, one of these L-band services like RTX or Atlas or, Veripost. And that could build a time series. Just it'd be really tight the whole time. Actually,
Yes.
now that I think about it, university out here, Central Washington University, is running PPP real time on a number of their stations out on the coast to process plate velocity. So it opens up a lot of doors and a lot of possibilities. Well, John, hey, I want to thank you for taking time out of your work day there.
It's hot out, so I got to sit in the air-conditioned truck for a while.
Oh, there you go. It's probably a little hot and humid there, and I hope you enjoy some good barbecue while you're out there.
Sure will, yeah.
Sure will.
Okay, well, thanks for the invitation, Gavin.
Thanks very much, John. Okay.